This is my conduction temperature project.
Alright, I had to change it up with my setup. This is the results from problem 5. This is problem 5 from the handout. For some background, I did calculations that I turned in separately. Here we are looking at a sphere that is generating heat and dissipating it into the environment. So we want to get rid of heat as much as we can and as fast as we can. This is doing it at a steady state. This is important. As I was talking about, I started with the heat conduction equation and worked with it to get a formula that would be a function of temperature and distance. The graph presented in front of you shows the temperature versus the radius of the sphere. It looks like the further you move away from the center, the cooler it becomes. This also looks like a first order function. The line is solid for a specific reason. It is because we are taking the data over all these points, not just a few specific points. So as I was talking about before, the heat conduction equation, there were several things that I needed to be successful with this. I needed boundary conditions and constraints. Some constraints would be like condition 1 and condition 2, or excuse me, I mean constant 1 and constant 2. Constant 1 was equal to 0 once I solved for it. Constant 2 was changing depending on what was changing in the equation. I had two boundary conditions. Boundary condition 1, which was the surface temperature equal to 383 degrees Kelvin, and the other one, being boundary condition 2, was the temperature at the radius of the sphere equal to 0. So here are some variations in the experiment. Here I changed 3 things about the experiment and conducted it 3 different times so that I'm able to compare it to itself. Parameter 1, I changed the initial surface temperature. As you can see, at the top right hand corner, this is the graph. They are all solid lines. It looks like no matter how hot you start, or whatever temperature you start at, it's always going to decrease at the amount that is similar to all the other ones. Moving on to parameter 2, thermal conduction change. This could mean the changing of the material. This one was very interesting. At the bottom right hand corner, you can see that no matter how hot you start, it will always come to the same temperature at the end. For parameter 3, this is energy generation change. Similar to conduction value change, no matter how hot you start, it will always come to the same temperature at the end. So here are the effects on how to improve. So what are we looking for? We're looking to get rid of heat. As discussed previously in the other slide, no matter what thermal conduction value you change to, it's always going to end at the same temperature. This is good because if you have a super hot inner sphere, that does not matter. So the material does matter. So some negative effects of this. When you change your different material, it might have a point where it could catch on fire like wood. Or if you have a higher surface temperature, you would not cool down as quickly.